Let's walk through a problem where we demonstrate a scenario where the claim is not the alternative hypothesis, but where the claim is better represented as the null hypothesis. All right, so let me bring up the scenario for this. Okay, and this is one of the rare cases where I actually get to present you with truly authentic data. So let me go ahead and share. So here's the scenario. I'll go ahead and type it up here so we've got a copy of it here in the whiteboard. So I'm going to do another example. So the claim is going to be in the null hypothesis, not the alternative. So that's the scenario that we're looking at here. Okay. And so let me go ahead and share the screen here. So what we have is a lot of times what I've done is I've created problems where I take the data, and I'm not lying to you. I generally use the data from a problem, but because I like to have variations or because they show up in exercises that students work on individually, I sort of simulate the data so it's similar to what was observed, but it's not identical. This actually is real data from a real study that I've actually took place in. So at one of the community colleges I used to work at many years ago, there was a placement test that we would give. And in fact, just in case you're curious about this, WAMAP actually evolved out of a conversation some colleagues and I had about 20 years ago about how very bad the placement tests that the school used as an institution to place students. We were so disappointed with it. And the fix we had at my school was we actually had students take a placement test at the very start of the term in the class to decide if they needed to be moved up a level or down a level. But WAMAP was actually designed to replace those systematic assessment tests, placement tests that were being used by a lot of institutions. And most people felt that they were very flawed instruments and very flawed tests. And so just a little bit of history there. But what we did is we would give a test, and the test was sort of designed that if students did really well, that meant that they were probably in the wrong class and they needed to go up a level. And if they did really, really poorly on the placement test, then they probably didn't have enough of the prerequisite content and they should probably be in the class before. So what we did is to be adequately prepared, a student needed to score 12 or higher on this 20-point quiz. We had a group of 58 students. I believe at the time it was actually 3 sections that I had. 3 of my sections took the placement test on the first day, and the average was 11.431, which technically is less than 12, and the standard deviation was 3.163. What we want to do is we want to test the claim that the class is adequately prepared for the course, and we'll use a fixed significance level of 0.05. Okay, so I'm going to go ahead and let me see if I can copy this because I probably just paste this into, I just realized I probably could have pasted it right into the whiteboard. Okay, so here's the scenario that we're working under. Okay, and again, the point for this is that what we're going to see is that this is an example of a situation where the null is going to become our actual claim. All right, so what actually is the claim? Well, if I'm approaching this from the standpoint of the teacher, my claim is that the class is adequately prepared. But now, what does adequately prepared in this case mean? Well, adequately prepared means a score of 12 or higher. So if the class is adequately prepared, then the average score should be 12 or higher. So sort of putting that out this way, that would mean so that means the average is greater than or equal to 12. Now again, this contains the condition of equality. It's greater than or equal to. So that's the condition of equality. So this actually is the null hypothesis. So this claim is best represented as our null hypothesis, which means the alternative hypothesis. The alternative hypothesis is the opposite of this, which is that mu is less than 12, i.e. that the students are not adequately prepared. All right, so there's our claim. Here's the claim is represented as the null hypothesis, and here is the the result that we're looking for. Now, again, if we just make a quick sketch of the scenario we're looking at, so we have that the average of the tests would be, the average of the tests is centered at, so it would be 12 or greater than. It's 12 or greater. So I wouldn't be surprised by values up here, but I would be surprised if I found values that were very far over here. And this is where the area here is alpha equals 0.05. Again, that comes from the fact that was given to us up here. So I'm just taking that from the fact that that was from the problem. That was just from the statement of the problem. All right. So what I'm going to do is I'm going to jump to Excel. So let me just summarize the statistics, the statistics from the sample. So let's summarize this. We have that the mean was 11.473. Sorry, 11.431. The standard deviation for our sample was 3.163, and our current sample size is 58. So what we want to do is let's use this information to get the p-value. I'm going to go ahead and just punch this into Excel because we can. That's probably the most straightforward way to do this. So again, we have the mean. So this is all information from the sample. We have our mean was 11.431. We have the standard deviation was 3.163, and the sample size was 58. So that's all information I'll record there. Okay. All right, so now let's do the t ratio. So I'll get the numerator. So the numerator is the, sorry, let me actually put, before I do that, let's put the population mean. The population value for mu was 12. All right, so the numerator then would be 11.43 minus 12. The denominator, that would be the standard error, or at least my estimate for the standard error, which is the standard deviation divided by the square root, sorry, typo there, square root of the sample size. Copy that formula there so you can see what I'm typing. Okay, so far so good. So my t ratio then would be, so the t ratio actually would be just those divided by each other. So negative 1.37. All right, so what I want to do is I want to get my p-value. So in this case, I want the t-dist function. I want my t ratio. I need the degrees of freedom, which is 1 less than the sample size. And again, the t-dist, we tell it, do we want a one-tailed or a two-tailed test? This is a one-tailed test, so I'll put in the value 1. And this is what I get in Excel. Excel doesn't like that, all right? Why does Excel not like this? Well, it turns out that the t-dist function is only designed to take positive values. So as I've typed this, it should work. It should work, but it doesn't because of the sign of my t ratio. So the fix for that is we always put the t ratio in the ABS function. So I'm going to include the ABS function, the absolute value function, and that gives me the p-value. That then actually does indeed give me the p-value that I'm looking for. All right, so I'm going to go back to the whiteboard for a second, and I'll record this information here. So our t ratio. So using this information, our t ratio was negative 1.37 and change. And the p-value for this, if we then calculate the p-value for this value, it was 0.088, which we can see is greater than 0.05, which was our alpha level. So the implication is we do what? What's the conclusion here? Or sorry, what's our decision? Fail to reject the null. Now remember, in our case, that was a good thing because our claim was indeed the null. So we're not rejecting it, we're not proving it, but we're not rejecting it either. All right, so here's the next end of class question. So I'd like you to state the conclusion in plain English. What's the conclusion in plain English? And I want you to use the flow chart. So I'll go ahead and put the flow chart back up here. So the next end of class question here is to restate the, put the conclusion, give the final wording for the conclusion for this scenario. Okay. And the hint I'll give you is, remember, our null hypothesis was that the mean was greater than or equal to 12.